I'm very glad to be here, so I'd like to thank all the organizers for giving me the possibility to give a talk on this occasion. So this talk will be about estimating the Hessian of some Hamilton-Jacobi equation from below. And this is a problem that has already been discussed, or at least introduced in the talk by Roland. In his multi-scale Bakri-Emery, you had to estimate the Hessian of Vt, and Vt was the solution of some Hamilton-Jacobi-Bellman equation. So I didn't come to this problem from the same motivation, of course. I would just like to start by explaining one of the reasons why this problem is kind of interesting. And maybe at the end of the talk, I will discuss some other reasons that motivated me to look into this question. So this is a very old result by Braskamp and Lieb, which is about the ground state wave function of Schrödinger operators. So if you don't know what the ground state is, it doesn't matter. In the next slide, I will give you a probabilistic representation. But the result is pretty nice. It says that if you have a potential V, which is k-square convex everywhere, point-wise, then the ground state of the operator minus 1/2 Laplacian plus V has the following decomposition. So you have essentially a Gaussian term, minus 1/2 over kappa x square. So the kappa in the convexity, you find it back here, times a function phi, and the function is log concave. So this is very nice. And you can view this as a sort of convexity propagation result. So if the Hessian of V is larger than k square, then the Hessian of minus the log of the ground state is larger than k. So how does the proof work? This is more or less the original proof they had. And here comes Hamilton-Jacobi already. So minus log of the ground state, you can represent it as the large time limit as minus the log of this expectation here, plus a constant that plays no role when you compute the Hessian. And it's the expectation of minus time average of the potential V computed in x shifted by a Brownian motion. And if you look at this expression, then you see that computing minus log of psi 0 amounts to compute the first marginal of a very log concave, of a big log concave vector. If V is convex, here you're computing the marginal of a very big log concave vector. And for this, there is a very nice tool, as Prokop-Landwehr, that tells you that if you have a big log concave vector, its first marginal is also going to be log concave. And if you apply a slightly more quantitative version of this, then you get exactly the result that I presented in the first slide. So the question I had is, okay, but what happens if V is not convex? Just Prokop simply does not work. So it's very well known that if V is just semi-convex, for instance, the Hessian is bounded below by minus epsilon. If T is large enough, the Hessian of psi 0 can blow up and go to minus infinity infinite times. So convexity propagates, semi-convexity doesn't propagate at all. So you need somehow to find a workaround, and you need somehow to find at least a partial generalization of Prokop. Also note that here I'm taking a limit at T goes to plus infinity, so you need Hessian estimates that are stable in time. So maybe obtaining an estimate for finite T is okay, but you want something that does not degrade or degenerate with T when T is very, very large. And now I would like just to sketch the link with Hamilton-Jacobi-Bellman equations, but this was more or less already done yesterday. If you define a function uttg as a minus log of the expectation of the same thing as before, just I start the integral at little t, and I also add the terminal condition, then, well, it's super classical. UTT is the only solution of the following AJB. So the linear part is just somehow heat equation. Then you have your source term or your cost v here, and then the nonlinearity is just a quadratic term, and the boundary condition is given by G. So in fact, this thing here is, if I understand things correctly, is more, I mean, it's similar to the renormalized potential that was introduced yesterday by Roland. The difference is that there was no V there, and the underlying, the Laplacian is not taken with respect to the unitary matrix. You have to modify the covariance matrix, which evolves in time. And we can read the result by Broskamp and Lieb in the following way. So if V and G are convex, then the solution of AJB stays convex at all times. So convexity propagates backward. And as I said before, semi-convexity does not. If the Hessian of V is just larger than minus epsilon, well, then the Hessian of UTT will go to can go potentially to minus infinity for finite time. So there is really a threshold at 0. Okay. So if you want to at least attempt to devise some notions that are weaker than convexity but still backpropagates along AJB, you cannot look just for semi-convexity, as we said, so you just have to impose some version of asymptotic convexity. So you will look for functions that are not pointwise convex, but in some integrated sense or average sense are convex. And one notion which is pretty useful that is borrowed from coupling techniques that have been developed to study the long time behavior of the Fokker-Planck equation is given a potential U to introduce its integrated convexity profile, which I call kappa of U. So what is kappa of U computed at some positive R? Basically, it's the best one-sided Lipschitz constant you can find for the gradient of U for points that are at distance R. So kappa of U larger or equal, kappa of R larger or equal than some alpha means that if I take 2 points that are at distance R, my potential behaves like a one-sided Lipschitz function, and the one-sided Lipschitzianity constant is exactly alpha. Another way of saying this, if you integrate the second directional derivative along a segment whose length is at least R, then you get exactly the same bound that you would get for a strongly alpha convex function, or for alpha semi-convex function. So the relation with classical convexities is pretty straightforward. So if kappa is always bounded below by some constant, then the function is semi-convex with the same constant. But here you have some more room to play, and we will see that by looking at profiles that are negative for small values of R, but positive for big values of R, you can actually include all reasonable perturbations of convex functions. Okay? All right. Okay, so let's say what is an asymptotically convex function, where we will say that U is alpha asymptotically convex if the profile is bigger than alpha for large R. So for points that are far, you behave more or less like an alpha convex function. And okay, it's often convenient to assume that U is not too concave, so the profile at 0 is larger than minus infinity. It just means that U has a lower bound on the Hessian that might be as negative as you want, but you have a pointwise lower bound. So this assumption is not always needed, but sometimes it's useful. So essentially, as I said, asymptotical convexity means that your potential behaves like a strongly convex function for distant points. And the hope you might have is that you can define some classes of asymptotically convex functions that are stable for the Hamilton-Jacobi-Bellman float, meaning that if you feed an asymptotically convex function to the as a terminal condition to AJB, then you keep the same profile along the solution.
The condition on the not too concave maybe will not be preserved.
Well, actually not too concave, at least for the kind of equation I'm looking at, will just get better. but I'm not looking at the general AJB. It's rather simple, the one I'm looking at. Okay, if V is very regular, yes, then you may run into troubles. But suppose V is kind of smooth, then it shouldn't be a problem. And okay, maybe one thing for those who really like Hamilton-Jacobi equations, so estimating the Hessian is somehow easy if you have an a priori Lipschitz estimate on the solution, because you can bootstrap an estimate on the Hessian from, well, this parabolic regularity techniques. But here somehow I'm really trying to get out of this perturbative regime. So I don't want to assume that my potentially small or Lipschitz in any sense. I just want to assume that it's a perturbation of something that can be as convex as you want, so you can grow as fast as you want at infinity. So in this sense, the estimate is not that standard. Okay, so let's just have a look at the convexity profile of some reasonable perturbations of convex functions. For example, if you take a potential U that decomposes as the sum of V plus W, and V is strongly alpha convex with positive alpha, and W is Lipschitz with Lipschitz constant L, and the Hessian of W is just bounded below by minus L, but of course L is much larger than alpha, so the resulting sum is not at all convex. Then you do a little computation and you see that the profile for R less or equal than 2 is larger or equal than alpha minus L over 2, which can be very negative, but then when you so here you just basically combine this bound and this bound, but when R is large, you can use also the Lipschitzianity, and you will see that essentially the convex part wins for large R, and the bad part just becomes less and less important. Or for example, you can take like these double well potentials, and you will see that so x to the power 4 minus L x to the power 2, and the profile is R squared minus L, is at least larger or equal than R squared minus L. Of course, this will be positive when R is large, and it will be negative when R is small. So again, by looking at profiles that are positive in infinity and not too negative at 0, you can encompass many perturbations of convex functions, or at least the ones that make sense in many applications. Okay, so here is a nice, I mean, it's one way to backpropagate convexity. So the theorem says that if you have an asymptotically convex V and also an asymptotically convex G, so I forgot to write this, and if you have any function f that satisfies a differential inequality, I don't want to get too much into the details of the differential inequalities, but I will show you later that actually you can find these functions. Then you can consider the following AJB equation, so the one that I've showed before. So if the terminal condition G has a profile that is better than R minus 1 times the terminal value of f, then the profile at 0, so of the solution at 0, will be better than R minus 1 f0 of R. Okay? So in some sense, you have a monotonicity principle for profiles. Okay, so if you take f to be constantly equal to 0, then you have the preservation of convexity. But here you have some more room to play with, and you can propagate backward profiles that are not everywhere positive. I will give some more examples in a while. Okay, maybe other questions so far? No? Okay. Let's have a look at some explicit calculations. So I set V equal to 0. This is the simplest case, but things can be done even with V different from 0. If I fix an L positive, you should imagine this as my convexity lower bound, so the worst value of the Hessian, so it should be minus L. Then you can define FL of R as a sort of rescaled version of the hyperbolic tangent of R. And you can see that the function FL for any value of L satisfies the differential inequality as an equality, and it's also independent of time, so there is no time in my function. So at least to this class of functions, the theorem I've shown before applies. So if you have a function whose profile is better than r minus 1 times fl for some L, then the profile of the solution will also be better than the same thing at any time. But the question is, okay, how weird are these functions? Can we actually capture enough profiles with this? And the answer is that, well, kind of yes. So if you have an asymptotically convex G that is not too concave, then you can always find an f of L such that its profile is better than r minus 1 f of L. So it will always be in one of these classes of profiles that are stable for the action of AJB. And actually, okay, the assumption that you're not too concave could be even further relaxed, at least a little bit, but I don't want to enter into the details of this. So the overall message is take a function that is not convex, but is a reasonable perturbation of a convex function, that it's in a class of functions that is stable for Hamilton-Jacobi. So you can track the Hessian along all the evolution of the equation, and it doesn't explode, it doesn't blow up. So for the case v equal to 0, of course, you could work with the representation of the Hessian in terms of covariances. Maybe also Roland had discussed this a bit yesterday, and this could be another way to deal with this. But the case v different from 0, I wouldn't know how to work with the covariance representation if I want bounds that are uniform in time. And also maybe one thing I would like to say that here all the focus is in sets that are invariant for the action of the equation. It's not just that you want to estimate the Hessian at some point, you just want to find sets that are stable, pretty much like in Precopa. Log concave vectors are stable under marginalization. Okay, so I would like now to spend some time, of course not explaining the full proof, but maybe just trying to give some ideas on how you do it. And the way I do it is by using coupling techniques along the characteristics of the Hamilton-Jacobi-Bellman equation in a way that is probably not the one that we are used to, at least in probability theory. And I'll try to explain why it's not the usual one in a second. Maybe well, this is just the theorem for the v equal to 0 case, but it's just the same statement that I've given before, so maybe let me just walk you through this again very quickly. So if you find a function that depends on time and I mean the distance that satisfies this strange differential inequality, you consider the AJB with terminal condition G. If the profile of G is better than r minus 1, the function at terminal time, then it's better than r minus 1, the function at any time, okay? Minus r minus 1, the function at any time. Okay, so as I said, let's have a little discussion about the proof. So HAB characteristics where they're nothing but the SDs was drift is given by minus the gradient of HAB. And what we are going to do, we are going to couple two of them, starting from two different points, by using coupling by reflection. So coupling by reflection is a relatively old construction. I think it's, well, it goes back at least to this paper, but probably it's even older. So what is it? So you choose a Brownian motion, the blue one, B, and you construct the associated characteristics. And then, this characteristics x starts at, say, little x. And then you construct the second one, x hat, with starting point little x hat, with a different Brownian motion, which is B hat. And what's the difference between B and B hat? So a picture is coming to explain this, hopefully. So the increments that are orthogonal to the line joining the 2 points at any time, they stay the same. But when you take the increments that are parallel to the direction joining x and x hat, you flip the sign. So you change the sign. So in words, dB hat is the identity minus 2, some vector et transpose times dB. And et is exactly the angle under which x hat sees xt. So x minus x hat over the norm of x minus x hat. And then what you're interested in is the distance process. Often RT is just the difference between the processes. So here is the picture that hopefully does a better job than my explanation. So here I'm kind of simulating an Euler scheme for coupling by reflection over a very small time interval t plus h. So this is, suppose I've constructed the process xt up to time t and x hat t up to time t. Then the process at time t plus h for xt will be the result of the sum of the, so you have to apply the Brownian increment, the blue one, and the drift, which is the red arrow. And then if you want to find where the process x hat will end up, well, it has its own drift. There is nothing to couple, it's just deterministic. And the Brownian motion, you take the blue increment, you decompose it into a component which is orthogonal to the direction joining x and x hat, and then a component which is parallel. The orthogonal component, you just take it, copy it as it is, and bring it to x hat. And for the parallel component, you change the sign. So this construction, which looks well, rather innocent, actually it's pretty useful in many contexts. You see, for example, here, of course I cheated a bit because I drew the picture in such a way that it works well. Sometimes it works in the opposite way. But you see here that by doing the reflection, I'm helping the two processes to get closer, because these arrows are pointing one towards the other, whereas if I was just doing the usual thing, namely synchronous coupling, these two arrows would just be parallel. Of course, I mean, if the blue arrow was pointing outwards, then the two guys would go further apart. But on average, if you measure distance carefully, this is typically a good thing to do. Okay, but let me just give a bit the overview of the proof. So you first build coupling by reflection, and then you introduce the rescale profile process. So the rescale profile process is basically the difference between the drifts, or minus the drifts of the characteristics, so the gradient of AJB, inner product with the angle AT. And the intuition is that more or less this process UT is roughly the distance process times the convexity profile of AJB. And so the key estimate in the proof is a monotonicity estimate that tells you that if you take U0, so you see that U0, at time 0, the two characteristics, I mean, there is no randomness. One is at x and one is at x hat. So U0 of x hat, little x hat, is more or less the profile of AJB at time 0. So this thing is larger or equal than something which is positive times RT times the profile of the terminal condition plus f of RT. So by our assumption, this thing is non-negative. So therefore, this whole expectation is non-negative. The assumption is the assumption we have on the profile of G. We assume that the profile of G is better than R minus 1 FT. So this thing here is non-negative. And then once you have these estimates, then the proof is over. Okay, so the whole game somehow is to get this monotonicity estimate. And here I would like to at least try to, for those like me who come from probability, I would like to try to give a bit of an idea on and try to explain how we use couplings in this construction differently from the way couplings are typically used to study the ergodic behavior of Markov processes. So typically, in a situation like the one we are considering, the typical use of couplings is the following. You know that your potential is a bit convex. Then you use a coupling to show ergodicity of the process, to show that the two characteristics, for example, get exponentially close in time. Okay? And here we do a bit the other way around. So what we want to understand is the convexity properties of the potential. So of course we cannot go along this way because simply we don't have this assumption. It's our goal to establish something like this. And I'm going to use a coupling, and I'm going to use something else. So I'm not going to work at first order. So I will not see how the evolution of the X processes is. I will look at second order. So essentially, we will establish an estimate which is similar to the fact that the distance between x and x hat is a convex function. So I have a second order estimate instead of a third order estimate. And from this and the coupling, I will infer the convexity of the potential. So you really go the other way around. And so the interesting part is how do you get this one? So of course, as I said, I don't have much information on the drift. This is what I want to study at the end of the day. So in order to get this, I need to have some more information on my characteristics. And this additional information is what people in control call the stochastic maximum principle, which basically tells us that if you look at the evolution of the gradient of AJB, this is a martingale. This is very classical if you interpret this gradient of U as the adjoint variable in the Pontryagin system associated to the AJB that we're looking at. Otherwise, you just take the gradient in AJB, do Ito, and you will end up with this, okay? So, in particular, this already helps us in computing a part of the Ito differential of my profile process. Let me maybe just go back very slowly. So, this is the process I want to study. And so I want to compute the Ito differential. So first I have to compute the Ito differential of this part. But the stochastic maximum principle tells me this part is just a martingale. Then I will have to compute the Ito differential of this other part of the angle process. And then I have a quadratic variation term, which is potentially quite harmful, because the quadratic variation term, because of the stochastic maximum principle, will contain a priori the Hessian of the potential, which is exactly what I want to estimate. So we better hope that this term is 0, and it's actually 0. So spoiler. So the final claim is that the Ito differential of the profile process is something negative in dt plus a martingale. So the profile process is a super martingale. That's the thing you care about. And as I said, let's try to understand a bit better why this should be true without getting too much into the details. So we want to compute the Ito differential of the profile. So the profile is this thing here. So as we said, stochastic maximum principle tells us that this is a martingale, so fine. Then we have to compute the Ito differential of the angle process. And here is the cute part. Because if you compute the Ito differential of the angle process, okay, there is something which may be a bit complicated, dt, and there is no dbt. So this is quite surprising, because if you take the Ito differential of the differences of the process, here we are along coupling by reflection, so not along synchronous coupling, it has a dwt term in the Ito differential. But the angle does not. And I'll try to explain this with some pictures. So I go back again to my kind of discretized Euler scheme along coupling by reflection. And all what I want to show is that the effect of the Brownian motion on the evolution of the angle, you just don't see it. So let's start again. I fix t, and I want to look what happens between t and t plus h. So first I have to add the orthogonal increments. But of course, when I add them, okay, the points change, but they move along parallel directions, so the angle under which one sees the other doesn't change. This is the same as in synchronous coupling. Then you have the reflection, and of course the reflection changes the distance between the points, but the reflection is just a movement that you do in the direction that joins x and x hat. So it doesn't change the direction. It changes the distance, but it doesn't change the direction. And then, yes, then you have to add the drifts, and this really changes the angle at the end, but the drift is a dt term somehow. So the dbt terms, they don't change the angle. So even if it's not synchronous coupling, the angle doesn't change. And this is why you don't have a dt, you don't have a dbt. And this is also why here, when you compute the eta differential, you don't have the quadratic variation term because one of the two terms does not have a dbt. And therefore, you can do eta formula as if it was a usual calculus, and you end up showing the claim, the claim that I had that the profile process is a supermarket. Okay, so this is somehow the main kind of ingredient in the proof. Then, of course, you have to see how to use the differential inequality that I stated on F in order to get the monotonicity, but this is somehow more standard. And well, I think in the interest of time, it's better not to discuss this. Okay, so now I would just like to somehow enter the second part of the talk. I would just like to discuss some applications of these results to the convergence of scaling algorithms in entropic optimal transport, which is one of the other motivations that led me to have a look at this problem. And of course, I don't assume that you neither like or know entropic optimal transport, so or Schrödinger problem. So I'm just going to give a very quick introduction. So essentially, the problem is a modification of optimal transport. So optimal transport, you minimize among all couplings of two given marginals the quadratic cost. And here we add also the entropy of the coupling against the product. And we add a constant here that we call the normalization. So, the larger the constant, the more prominent the role of the entropy gets. The smaller the constant, the more prominent the role of the linear cost becomes. And there is a nice result that's kind of also very old that tells you that the optimal coupling, pi star, has a nice form. So it's the exponential of the cost minus the cost times the exponential of minus the sum of two functions. One function phi star that depends only on the first variable x, and one function psi star that depends only on the second variable y. And phi star and psi star are called Schrödinger potentials, and they are proxies for the Brenier potential. So when t is very small, they are supposed to converge to the Brenier potentials. Okay? So for various applications in machine learning that I don't know very well, to be honest, but that are quite prominent, I'm told, you want to compute these potentials. So typically what you want to do in machine learning, you want to solve optimal transport, where this is difficult, you regularize a little bit, you add the entropy, and the entropic problem you believe it to be much simpler to solve. And the reason why the problem is much simpler to solve, at least in principle, is that you can use a particular algorithm that is called the synchron algorithm. And the synchron algorithm relies on a system of equations that captures the potentials, which is called the Schrödinger system. So the Schrödinger system tells you that if you write your marginals in Gibbs form, so mu is exponential of minus u mu, and nu is exponential of minus u mu, then the Schrödinger potential, phi star and psi star, are characterized as the only solution of the following system of coupled Hamilton-Jacobi-Bellman equations. So phi is the potential for mu minus the solution of AJB at time 0 with terminal conditions, with terminal condition psi. Again, I am the setting in which v is equal to 0, so I don't have the running cost. And psi is u nu minus the solution of AJB with terminal condition phi. Okay. And Synchron algorithm just solves this system as a fixed point, so in an iterative way. It does the following thing. You start with any psi 0, and then you choose your stopping criterion. And then at each iteration, suppose you were able to compute psi n and phi n. Then you compute phi n plus 1 by feeding in psi n to AJB, compute the solution, change the sign, and add the potential for mu. Then you get phi n plus 1, and you do the same. So you compute psi n plus 1 by feeding phi n plus 1 to AJB, compute the solution, change the sign, add the potential. And if you repeat this, of course, in the limit, you're supposedly getting a fixed point, and then you have computed the Schrödinger potentials. So you can view this algorithm in many different ways. You can view it as a sort of iteration of Bregman projection. You can view it as a dual block coordinate descent, where dual refers to the dual of the Schrödinger problem. There are millions of nice interpretations. And thanks to the estimate that I've shown before, you can show that if your marginals are such that the profile of the associated potential are asymptotically convex, then there exists a value of the regularization T0 such that above this value, you have exponential convergence of the gradient of the iterates towards the Schrödinger, to the gradient of the Schrödinger potential in some L1 sense. And you can have explicit constant. Also, the value of T0 can be explicit. You can also have convergence on the primal side for the plans. And also, there's a funny thing that I've been talking all the time about convexity, but in Synchron, if you also have some information about the concavity of your potentials, so they're not too convex, then this also helps speeding up the algorithm. And the intuition behind this is that, no, I still need to learn how to use that. Let me go back to the system here. You see that here, what makes the algorithm a bit tricky to analyze is that suppose you know that psi is very, very convex, then you can expect the solution of AJB to be very, very convex, but then you change the sign. So the convexity of psi will actually contribute to the concavity of phi and vice versa. So it's not enough just injecting a lot of convexity in the potentials to get, well, actually it is enough as the result shows. But if you also can put your hands a bit on the semi-concavity of your potential, you can improve the results in the sense that you can improve the rate, and you can also lower the threshold after which you have exponential convergence. And well, as a byproduct, you will also get that the profiles of the iterates of Synchron algorithms are always asymptotically positive. And the nice thing is that the result I've shown before is the first one that shows the exponential convergence of Synchron on RD. Because so there's been a lot of work about exponential convergence of Synchron, but it's always on compact spaces, and the rate of convergence heavily depends on the diameter of the space. So in particular, none of these results would apply to the quadratic cost. And somehow, by doing this, you can take a first step in the exploration of what happens for unbounded costs. And okay, after our result, there has been some new contributions by some other people who took a different approach and managed to establish somehow exponential convergence of Synchron in an unbounded setting, but the presence of this threshold T0 it's still there. Actually, you can only get rid of T0 if you assume that your marginals are more than convex. So the kappa of R is not only positive, but goes to plus infinity. But this is, for instance, it eliminates Gaussians from the analysis, which is maybe a bit, well, not what you would like to do. Okay, so maybe let me almost finish actually on the ground state energy. So I want to go back to the original problem. So the original problem was to see if it was possible to extend a little bit the result by Braskamp and Lieb about the convexity of the ground state of Schrödinger operators. And actually, yes, it turns out that you can do it by the methods I've discussed a bit in the talk. So you just have to assume that your V is asymptotically strongly convex, in the sense that its profile is positive at infinity. And then once again, you have to find a solution F to a certain differential inequality that involves the rescale profile, so R kappa V of R. And if you can find a solution to this, a subsolution to this equality, then you have that the ground state wave function psi 0 is such that the profile of minus its logarithm is larger or equal than minus R minus 1 f of R. And in particular, the profile of the ground state is asymptotically convex, and you also get all kinds of functional inequalities because, of course, once you have a measure which is asymptotically strongly log concave, you get all the functional inequalities you want. You have some nice applications of this to Feynman-Katz semigroups or other things. Maybe I would just like to make one little comment. So I've discussed about couplings, I've coupled characteristics, but what is really the gain in reflecting? So I try to explain what you gain when you do reflection in terms of what happens when you study the long-time behavior of Markov processes. So when you do the reflection, it helps because half of the times it helps the processes getting closer. But this is not, of course, what I was doing with the couplings. So the reflection actually helps because if you work just with the classical synchronous couplings, you can also get a result of this kind. But you don't have this second derivative term in the differential inequality. So without this one, the solutions F that you can construct to satisfy this differential inequality are much less. So still you can recover the result by Braskamp and Lieb with a nice, nice for those who like this, but with a probabilistic argument, just synchronous coupling along the characteristic of AJB. But you cannot get this F, the second derivative of F. And having this is exactly what makes it possible to get away from pointwise convexity and to go to this relaxed notion of convexity that I have discussed during my talk. And maybe a bit as a further outlook, all these estimates about how convex is AJB, they might be useful in other contexts. For example, in stochastic control, you may often be interested in studying the long-time behavior of solutions to stochastic control problems. And solutions to stochastic control problems typically involve the gradient of AJB in the optimal control, in the drift. So if you want to study the long-time behavior, then you want some one-sided Lipschitzianity of the drift of your optimally controlled process. Then at the end of the day, you just want some Hessian bounds on AJB. And also, recently there is a lot of nice activity about constructing Lipschitz transport maps between probability measures in the spirit of Caffarelli. And so there are many ways of doing this. For example, there's this Vollmer process. There's, what Roland discussed, and for example, localization. And essentially, these bounds here, you can just plug them in, for example, into the Vollmer process approach to get the existence of a Lipschitz map, simply because the Vollmer process is, if you write it differently, it's just the characteristic of AJB. So the sufficient condition to have a Lipschitz transport map in the Vollmer process approach is the one-sided Lipschitzianity of the drift, But the drift is the gradient of HAB, so you can just take these bounds and use them in that context, and they would give you something. Yeah, I think I would like to stop here. Thank you very much for listening.
Thank you for the talk. So do we have questions?
Do you think there may be a fully analytic proof of this?
Yes, so, well, of course, yes, at some point there will be, but I've spoken with people who are much more into analysis, and it seems that, so, okay, these ideas of using couplings can all, for estimating the derivatives of HAB, if you implement them at the level of the first order derivative, so to get Lipschitz estimates, there is kind of a clear bijection between coupling methods and viscosity solutions, what people in the theory of viscosity solutions. At second order, it seems less clear. So if you want to study two-sided bounds for the Hessian, I think more or less you can already write down what the corresponding PD argument would be. For one-sided bounds, I was discussing with Alessio Porretta, who is very much into these things. So a posteriori, yes, you could write a PDE argument, but somehow this kind of, yeah, but somehow, so yes, the answer would be yes. You can take the probabilistic argument and at the end of the day cook up a PDE argument, but somehow the PDE people had not looked into, at least from what Alessio says, had not looked into this type of estimates. As I said, what I've seen most of the times in this theory is that you often start with the Lipschitz estimates, and then from the Lipschitz estimates, you bootstrap Hessian estimates. But here, this is a perturbative approach, and here somehow you kind of want to get away from this. But yes, I would be surprised if there is no PDE way of doing this.
Pretty much in the same method. It seems to me that this only works for Laplacian and pure Brownian motion in the Hamilton-Jacobi-Bellman. If you have volatility, or you can construct a better reflection.
No, I think there is some room to play. I did not explore this in full generality. But people know how to do coupling by reflection when there is a diffusion. The question is, can you carry out the second order analysis? This is the question that it seems more difficult. For sure it works, for example, for fractional Laplacians. Because in the end you replace Brownian motions with alpha stable, Levy, and more or less you can do the same.
But the key is that there's no GPT there, right? That's the whole key.
In these estimates, for the moment, yes. But even if you have even yes, for this argument to work so far, yes. But it's not impossible that you can. I mean, I guess it's not over yet, but haven't gone in this direction. So for sure you can do alpha stable, and for sure you can try, if you want to go to the mean field setting, you can try with component-wise coupling by reflection. To obtain estimates that are somehow independent of the dimension. So sorry, even here there is no dependence on the dimension in the estimates, but it's often like this. So there is not dependence in the estimates, but when you look at concrete models, it's hidden. There is because say the Lipschitz constant, when you take the sum, it just goes like the number of summands. So there is a hidden dependence. So for sigma, something probably can be done. But so as I said, I think there is potential to go beyond this. But I have not fully explored all what can be done.
For the long-term behavior, the reflection coupling is probably one of the best ones for dealing with the long time. But in fact, any coupling will be sufficient in order to get some estimates. And here, what is the impact of the reflection with respect to other coupling?
Yeah.
It's not a synchronous one.
Well, the reflection has this other big advantage that you don't have the, so maybe this, okay, thank you, this is nice. It allows me to practice the arrows again, back and forth. It has this, I would say this is the big advantage. That the angle process in coupling by reflection does not have a DBT. And you see that this is exactly because you do, the orthogonal increments are kept, and you only change the parallel increments. If you cook a coupling where these ones are, where you change these ones, then the whole thing kind of breaks down. So I think this is the main advantage. Because, so what is the harm of having a DBT part that, the harm is that, yes, is that you will have to do a quadratic variation, and you will have this in the eta differential of the profile, but this is exactly the object where you know nothing about a priori. So I see, so to me the advantage of doing the reflection is exactly that the angle has these nice dynamics. And this is only synchronous and reflection as far as I can tell.
You can add a parameter between, you can do any convex.
Yes, you can do. You can also resample independently the parallel one.
Between synchronous and reflection, there is a line of coupling.
Ah, yes, this you could do. Yes.
Please ask a question. But synchronous coupling also we don't have this.
Yes, but with synchronous, yes, also has this nice property, but synchronous coupling will not allow you to have this second order term in the differential inequality, which is exactly what allows you to propagate back, to construct solutions to the differential inequality that can deal with profiles that are not positive everywhere. So synchronous coupling would work, and it would prove you the Braskamp-Lieb result that I showed at the beginning.
And this expression, does this come from this kind of twisted metric from Eberle, or?
No, exactly. No. It's not the twisting metric from Eberle. It's any f that satisfies this.
Okay.
So of course, as in Eberle, there is the idea that a concave f will help, and you see, in fact, that if f is concave, then here you pick up something non-positive, which will help make the whole thing non-positive. But this f is not, also because to have the f, you need to know something about the drift, and here it's really the case where you don't know anything about the drift. So if you want the f, it depends on the v, and not on the solutions, because you just don't know the solution. So it's not the function by Eberle.
Is there a last question? Okay, if not, then thank you again, Giovanni.